In this lecture, we are going to talk about azoles, both 1,3 azoles and 1,2 azoles. In the first clip, we will mention about the ring synthesis of 1,3 azoles. For 1,3 azoles, there are three important classes: imidazole, thiazole, and oxazole, containing nitrogen, sulfur, and oxygen respectively. As we mentioned in the first lecture, we know that this nitrogen is not nucleophilic or not basic because the lone pair of this nitrogen is used in the localization into the ring to make it aromatic. However, the lone pair of this nitrogen remains nucleophilic or basic because this is in sp2 orbital that can be used to attack something else. Same for thiazoles and oxazoles. You may have seen some drugs that contain these 1,3 azoles, ranging from Parkinson's disease, HIV, and hypertension, and so on. The most common strategy for synthesizing 1,3 azoles is to start from the alpha halocarbonyl compound, which will provide two electrophilic sites. The first one is the alpha halo position, and the other one is the carbonyl group. And another nucleophilic species is the 3 atoms unit supplying a C2 and 2 heteroatoms, which are both nucleophilic. So these can react with the first component in order to form 1,3 azoles. And if you look at thiazoles at first, which contain sulfur and nitrogen, that 3 atom unit can be in the form of thioamides, where first the sulfur can attack the alpha halo position in the SN2 manner, and after that condensation between amines and carbonyl group with a loss of water molecule lead to the formation of thiazole. If you don't want the substituent on this 4 position, like in this molecule, you need to start from alpha haloaldehyde, but we know that aldehyde is not so stable, so sometimes you need to mask it in the acetyl equivalent. And if you want some substituent on the C2 position, you can install it in the first place. And one of the most common substituents is the amine group, so that in this time you can start from thiourea as your nucleophile. For the synthesis of oxazole, which contain oxygen and nitrogen in the ring, you may start from an amide, which can provide both of the heteroatoms. However, we know that amide is not so reactive, so you might need to force the condition a little bit by, for example, heating up. And for imidazole, this molecule contains both nitrogen atoms. The strategy that you can use can start from amide as well, but in this case, instead of using oxygen as a nucleophile, you can add another heteroatom source in the form of ammonia, which will condense with the carbonyl group to provide the second nitrogen in the ring system. Another popular strategy for synthesizing imidazole is to use guanidine, which contains 3 nitrogen atoms. So these 2 free nitrogen atoms can react with the alpha halocarbonyl compound to form imidazole ring. However, if you use this strategy, you are going to end up with a substituent, nitrogen substituent on the molecule. So if you want it in your final product, this might be a useful reaction to use. Another way to synthesize oxazole is by cyclizing dehydration of alpha acyl amino carbonyl compound. So if you look at the name, the carbonyl group is here in the molecule, and it has the amino group alpha to it, which is this component, and the acyl group attached to the amino group here. If you dehydrate this molecule twice, you are going to form the oxazole, which is equivalent to the cyclization of 1,4-dicarbonyl compound into a furan ring. Okay. If you look at this example, the Robinson-Gabriel synthesis, starting from the alpha acyl amino carbonyl compound, you can use the lone pair of the nitrogen, help attacking the ketone, and now once you closes the ring, you can make it aromatic by removing this water from the molecule, and then you get the oxazole. You may start from scratch. For example, in the second example, you can use the amine to react with this iminium ion to form the imine. And then under the basic condition, you can remove the proton here to make it nucleophilic. And now this can attack the ester group in order to form the enol. And this enol can act as a nucleophile to attack the imine group that contains the leaving group here. So attack here, out here, and kick out the leaving group. So at the end, you are going to form the oxazole from the reaction. The last example for the synthesis of 1,3-azoles that I want to show is from isocyanides. For example, the torsyl methyl isocyanide here. Torsyl methyl isocyanide. So after the reaction, you are going to provide the 3 atoms unit containing the nitrogen, one of the nitrogen in the ring. And the torsyl group is important as a leaving group in this step. Okay. In order to form the 5-membered ring, you need another 2 atom unit, and this atom you need to have it containing the heteroatoms of your choice, either it as an oxygen, nitrogen, or sulfur. If it's oxygen, then it can be an aldehyde or ketone. For nitrogen, it can be an imine, and sulfur can be thioketone or something like that. Okay. If you look at this example, the torsyl methyl isocyanide together with a base can react and remove the proton at the alpha position here. So this can act as a nucleophile to attack the imine, and upon attacking, you are going to form the amine, which is now nucleophilic, and this amine is going to react with the terminal carbon, which has the carbene character, as I used to mention. Upon attacking, you are going to form the anion here at the sp2 carbon. This anion can remove the proton of this position of another molecule and eliminate the torsyl group out to form the imidazole ring. If you use just a simple methyl isocyanide instead of torsyl methyl isocyanide, you don't have the leaving group here, so you need to put the leaving group in your another species. In this case, the methoxy group in this of the ester can act as a leaving group, or in the second example, this chloride can act as a leaving group. So if you look at the mechanisms, first you are going to deprotonate here to make it nucleophilic, and this is going to react and kick out the chloride. and from here this can becomes enolate and attacking the terminal carbon here to form the negative charge here, which can accept proton from something else. And then you got the oxazoles or thiosoles using this kind of strategy.